Okay, so let's look at our second example of a hypothesis test. In this one, a cosmetic company fills its best-selling 8-ounce jars of facial cream by an automatic dispensing machine. The machine is set to dispense a mean of 8.1 ounces per jar. Uncontrollable factors in the process can shift the mean away from 8.1 and cause either underfill or overfill, both of which are undesirable. In such a case, the dispensing machine is stopped and recalibrated. Regardless of the mean amount dispensed, the standard deviation of the amount dispensed always has a value of 0.22 ounces. A quality control engineer routinely selects 30 jars from the assembly line to check the amounts filled. On one occasion, the sample mean is 8.2 ounces, and the standard deviation is 0.25 ounces. We want to determine if there is sufficient evidence in the sample to indicate, at the 1% level of significance, that the machine should be recalibrated. So let's start with our null hypothesis. Remember, it's always the mean equal. In this case, we want the mean to be 8.1 since that's what the machine needs to be calibrated to. So our null hypothesis is that the mean should be equal to 8.1. Okay, now, since it says up here that we do not want it to underfill or overfill, that means that our alternate has to be that the mean is not 8.1. We want it very close to 8.1, and we don't want it that's in either direction away from 8.1. So there's our alternate. The mean is not equal to 8.1. All right, so let's identify other things. We've got 30 jars in our sample, so that's our N. Our mean is 8.2 ounces, so now that I stopped my computer from singing, the mean is 8.2, and the standard deviation is 0.25 ounces. And we have a 1% level of significance, so alpha is 0.01. Now we need to calculate our test statistic, so Z is our mean of 8.2 minus mu, which in our null hypothesis is 8.1, and we want to divide that by the standard deviation of 0.25 divided by the square root of 30. All right, so now if we divide 0.25 by square root of 30, we get 0.05. And if we do our final calculation of 0.1 divided by 0.05, that gives us a test statistic of 2. All right, now, since this is a two-tailed test, and anytime our alternate hypothesis is a two-tailed test, we are going to have two rejection regions on the left and the right. So we're going to take our alpha value and divide it by 2. If we do that, it becomes alpha divided by 2, 0.01 divided by 2 is 0.005. So we're going to go to our table and first look up Z of 0.005. So notice if we look for 0.005, here's 0.0051, here's 0.0049, 0.005 is directly between these two, so that's directly between negative 2.57 and negative 2.58, so we'll go to negative 2.575. So our rejection region is going to look like this. So our bell curve looks like this. And notice here's negative 2.575. And over here, by symmetry, we're going to have another region, 2.575. And we're looking for anything to the left of negative 2.575 will be rejected. And anything to the right will reject of 2.575 will reject the null hypothesis. All right, but our test statistic gave us 2, and 2 would be in here somewhere to the left of the 2.575 and certainly way away from this value over here on the left. So it's not in the rejection region. Since 2 was not in the rejection region, we will fail to reject the null hypothesis. And in this case, alpha is 0.01. So there is not enough evidence for us to conclude that the machine needs to be recalibrated. It appears to be properly calibrated at the moment. And that's what it means by we didn't have to accept this alternate hypothesis. It appears to be that the mean is 8.1 at the moment.